Hi folks, Mr. Ackerman here. Thanks for watching today. The topic of today's video is friction forces and Newton's laws. So we're moving on in Unit 2. We are currently on lesson number 3, section 2.4 in your textbook. You'll be happy to know that if you have been following along with the previous section 2.3 and you've understood how we solve Newton's second and third law questions, then today's lesson is really just an add-on to that. There's not a heck of a lot of new stuff. You're really just learning one new idea and then going in and using that in problems that are similar to what you've already been doing. So as usual, make sure you're taking some notes in the textbook as you go along and looking at those sample problems. Also, there's a reference to your course pack where we talk about inclined planes with friction this time. Some questions for you to try in class, and we're also going to do a little demo that is also found on page 113 of your text. Finally, a few questions for you to try at home. And just a little note here that even though fluid friction and Bernoulli's principle is part of the textbook's treatment of friction, we just might leave that out this time officially to save time. But I do encourage you to read it. It is interesting. So what are we going to be talking about in today's video? We're going to look at how to incorporate friction forces into our problems involving Newton's laws. We're going to learn about this thing that you probably remember from grade 11 called the coefficient of friction, and we're going to see how we use it to calculate the force of friction. And hopefully, if we just scoot down to here, to the learning goals and success criteria, I'll let you read most of these on your own, but one that's really important, and a lot of students get tripped up here, you got to be able to distinguish between this thing called the coefficient of friction, that's this up here, the coefficient of friction and the force of friction. Please make sure that before you finish today's video, you clearly understand that the coefficient of friction is not the same as the force of friction. We're going to finish off with some examples of grade 12 type problems where the normal force and gravity are not the same, and you're going to see why that's important in just a minute on the next slide. So here we go. I'd like you to think back to grade 11 where you were first introduced to the force of friction. In some questions they just tell you what the force of friction acting on an object is, but let's take a step back for a moment and think about what really causes friction. If you think about friction, let's take a common example. Imagine you're standing outside in the cold in the winter and you rub your hands together to warm them up. Think of the things that you do to achieve greater warming. Well, you probably want more friction between your hands. So one thing you might do is rub faster. Another thing you might do is press your hands together harder in order to create more friction and heat and get the desired warming effect. Well, when you press your hands closer together, what are you really doing here? If you think about it, you are pressing two surfaces into contact harder than if you press lightly. And what does this do? Well, it actually causes the hands to react with greater force to one another. This is a reaction of two surfaces that are in contact. Can you think of what force I'm hinting at? It's the normal force. In other words, the friction force depends on the normal force. So I'm just going to write that in here. Now, is the friction force equal to the normal force? No, it would be kind of strange if in every situation that we could encounter, the friction force equaled the normal force. What often happens when you have two variables that are dependent on one another is one of them is often equal to a number, a constant, times the other. And this constant, if you think back to grade 11, is actually given a Greek symbol, and the Greek symbol that we use is the letter mu. All right, so do you remember that? Maybe you remember the formula FF equals mu times Fn. This was taught to you in grade 11, and it's still true in grade 12. Just one thing that some of you might be noticing, the friction force in terms of its direction isn't necessarily related to the normal force. So what we're really talking about here are magnitudes. These absolute value brackets mean magnitudes, so we don't actually talk about the direction of the friction force and the normal force. We're talking about the magnitude. Okay? If you're rubbing your hands together, the normal force points perpendicular to the palms of your hands, but the friction force would be running along your hands parallel to the palm of your hands. So once again, it's not the direction in here, it's the magnitude that we care about. Anyway, this Greek letter mu, the coefficient of friction as it's called, is different for different surfaces that are in contact. For example, you can imagine if you rub your hands together when they're dry, you'll get a certain amount of friction. But if you did the same thing after you had, I don't know, coated your hands with oil or Vaseline or something, you'd get less friction. So it's not just a matter of having hands in contact, it's a matter of what substances are in contact. So in your book, this book would be Physics 12 by Nelson. It's the book we're going out of, and it's the book I took this table from. You're going to see for various pairs of materials in contact, in the first column here, what is the mu value that they have, which goes into this formula. So for example, rubber on concrete. Here we're thinking of tires of a car. Rubber on concrete, rubber on asphalt, dry road conditions. Here are the mu values. And right away you're going to notice, well, there's two mu values. There's the mu with a subscript s and the mu with a subscript k. What do these refer to? Again, looking back or thinking back to grade 11, maybe you remember that the s stands for static and the k stands for kinetic, as in static friction and kinetic friction. What are these? Well, to give you an idea of what we mean by static and kinetic friction, I'd like you to try a little experiment at home. This will be very easy to do. You're probably watching this on a laptop or maybe some other device like a phone. Just put your phone on the table where you are right now, or your laptop on the table, whatever you're using. So let's say this is the surface here, and here's your phone or your tablet or your laptop, whatever. And what I want you to do is take your hand, there's my hand with hopefully 4 fingers and a thumb, I don't know. Give a push, a very, very slight push to the right. Give this F applied. And I want you to purposely push so lightly that the phone or the laptop or whatever actually doesn't move. Push so lightly that it doesn't move. Why isn't it moving? You're applying a force. The reason it's not moving is because there's a friction force opposing the motion. And assuming your device is not moving, that would mean that the friction force is exactly balancing the applied force. Because it's allowing the object to stay stationary or static, we put a little s down here. And if we're trying to calculate this friction force, we say it's equal to the mu value. We'd have to look in this table. What's your phone made out of? I don't know, maybe you've got a rubber protective coating on it, so we could look for rubber in there. And maybe it's on a wooden table. Let's see, do they have rubber on wood here? They've got rubber on ice, rubber on steel, rubber on asphalt. I guess this table is incomplete. We can't really use it to find the mu value for this little experiment that you're doing, but you get the idea. You'd find this somewhere in some data table that I'm sure exists. Probably look for it online if you want. Mu times the normal force. Now what is the normal force in this case? Well, you've got a phone or your laptop and it's sitting on a table, and there is a force, I'm sure you know, of gravity acting down. So we could do something like this. That's going to be equal to mg, the mass of your phone. And of course, going up would be a normal force. And assuming your phone is not accelerating upward or downward, it would be safe to say that the normal force is equal in magnitude. Sorry, I give that a double tick mark so I don't confuse it with the single tick marks over here. And double tick mark for gravity. So what you could actually do here is, using a little bit of logic, figure out that the normal force here is equal to mg. So you'd end up with mu mg, right? Anyway, getting back to my point was sometimes you push so lightly the thing doesn't move. In that case, use the static friction coefficient. However, now repeat the experiment and push a little bit harder. And of course, it shouldn't be too hard for you to begin to accelerate your phone in the direction of the applied force. There isn't that much friction acting on the phone. Now you're going to be sliding across. There's going to be movement. So now you go to the kinetic friction coefficient. and we'd actually have to redo our calculation, our analysis of what's going on. Looking back at the data table here, you can see if you compare the mu values for the same situation, like rubber tires on concrete, static 1.1, kinetic 1.0. Look at steel on steel, 0.6 for static, 0.4 for kinetic. Look at, for example, wood on dry snow. So think about a snowboard or skis made of wood going over the snow. 0.22 for static, but the kinetic values always seem to be less than the static values. And why is that? Think about it for a minute. Pause the video if you have to, but assuming you're back now after thinking about it, if you think about it, when an object is static and is sitting on a surface, it has a little bit of time for the molecules in its surface to make very weak bonds with the molecules on the surface that it's sitting on. And the longer it sits there, the stronger these bonds can become. And so to get something moving when it's not moving yet, when it's static, actually requires a little bit more force than if it's already moving. And for this reason, the static friction and the static coefficient values are usually going to be higher than the kinetic values. Just to make one more little observation before we get into some problem solving, you might be thinking, if you're thinking back to the very first force video that we did where we talked about the fundamental forces, do you remember what they were? They were, let's see, give you a little quiz here. They were gravity and the electromagnetic force, and then there were two nuclear forces. There was the strong and the weak. And if you remember, I made the argument to you that every single force in the universe falls into one of these four categories. In other words, these are the really fundamental forces. Which one is friction? Well, it's not gravity. Gravity is its own force. The nuclear forces exist only within the nucleus of an atom, and unless we're dealing with radioactive decay or nuclear fission or fusion or something like that, we're likely not dealing with nuclear forces, which leaves by process of elimination the electromagnetic force. Is friction an electromagnetic force really at its heart? It is. The reason there's friction is because when two surfaces come into contact, they attract one another. There are weak bonds that get formed between two surfaces, sometimes strong bonds. Think about glue holding two pieces of wood together, for example. And these forces prevent them from slipping past one another, which leads to friction, or at the very least, they make it hard for things to slide past one another. Friction is the result. All right, now that we understand friction, let's go into some problem solving. The first one, which I'm not going to spend very long on, is sample problem 1, which is already in your textbook. So I'm not even going to solve this for you. You can look at what they did. However, I am going to point out a few things. They talk about a crate sitting on a floor. Okay, so I'm just going to draw this out. Try to draw a straight line, hopefully. There we go, or a horizontal line. So here's the crate. It's sitting on a surface. If I begin analyzing some of the forces right off the bat, I know that there is definitely going to be gravity, so I should put that in right away. There's probably going to be a normal force. We are sitting on a surface here, so I'm going to write that in. And then reading a little bit more, it says that they ask you for the force of friction and the acceleration if a horizontal force of this amount and then that amount get applied. So let's put in an applied force, use a different color for that, supposing the force is going to the right. And of course, knowing that there's friction in this problem, the applied force going forward would have to be met with a friction force which is going backward. So there we go, F, F. Now, how do we go about solving this? Well, first of all, a couple things to notice. There is no upward or downward pushing, so the normal force and the gravity force will be equal, which right away, since Fg is equal to mg, it tells me that Fn will also be equal to mg. This is kind of a grade 11 style problem. So I'm just going to write grade 11 there, just so you'll remember. Okay? You're applying a force of 75 newtons in the first case, so let's write that in. 75 newtons in the direction indicated. And then there's friction, which according to our formula learned in grade 11 is FF equals mu Fn. So we go back here and we say this is equal to mu times Fn, but we know Fn, which is equal to mg, so we can actually write in this. And now let's take a look. The mu value, it says mu s is 0.45, mu k is 0.41. Okay, that makes sense. Usually mu k is less than mu s, but which one do I use here? Well, let's start looking at the force that's being applied. The friction force, the applied force rather, is 75 newtons. And if you take a look at the static friction force, the force that prevents slipping when the object is at rest, let's just calculate what that is. If we go with static, just to begin, we'll have mu s times mg. That's going to be 0.45 times the mass, which is 18 kilograms, times 9.8, which is the local value of g. I'm just going to plug this into my calculator now. And what do we find? 0.45 times 18 times 9.8. I get 79 point something, 79.38 newtons. Well, guess what, folks? The applied force was only 75 newtons. So you can make the conclusion that this pushing force is not enough to overcome static friction. In other words, what will happen? What will be the acceleration in part A? Well, the acceleration will be 0. There will not be enough applied force to overcome static friction. Let's jump to part B. Now they say, suppose a horizontal force of 95 newtons is applied. So I'm going to leave you with this to follow along on your own. But if this gets increased to 95, I think you can clearly see we're easily going to overcome the 79.38 Newton friction force, and now the object will begin sliding. At which point you have to be careful. We're now no longer dealing with static friction. You're going to have to shift to not mu s, but mu k, which was given up here as 0.41. So you'll have to redo this problem with a slightly different friction force, which is going to be less. And they do that in the book, so I've said enough here. I want to pick up the pace and move on. All right, here we go. Next question. Let's look at a grade 12 style question. I call these grade 12 style because, as you're going to see here, the normal force is not going to be equal to gravity the way it was before. Let's have a look. It says an adult is pulling 2 small children in a sleigh over level snow. I begin drawing. Let's do our best here. There you go. There's a sleigh. There's some children. Looks like they're standing up. That's not safe. We want them sitting down, right? There we go. Happy, safe children. Okay. The adult is over here, and I don't know, maybe this is mom who's taking them out for a little walk. Okay. The angle of the rope is 23 degrees with the horizontal. Excuse me there. 23 degrees with the horizontal. So if I sort of imagine to myself, there's the vertical, and there's the horizontal, then the angle I'm looking at in here, in which I haven't left myself much room to draw, 23 degrees. Here's y, and there's x. Okay? They tell you that the coefficient of friction between the snow and the sleigh is 0.11. Kinetic friction, of course, because mom is pulling these kids in the sleigh. They are moving. Calculate the magnitude of the tension in the rope in order to keep the sleigh moving at a constant velocity. That's important information. V is constant. They don't tell you what value it is, they just tell you that it is constant. So what do? Do we assume a value? No, we've got to think of Newton's laws. Newton's first law, which I'm going to abbreviate as N1, tells us that if we have constant velocity, then what? Can you think of what it is? Then it means that the net force external is 0. In other words, things will move in a straight line at a steady pace unless there are unbalanced forces acting on it. In this case, the net force is 0. So that's an important piece of information to keep in mind. Now, Since we're going to be analyzing forces, we have to draw a free body diagram. So I'm going to put that in over here. I'm going to put in my directions one more time. Oops, missed. There we go. All right, so we've got Mom pulling at an angle 23 degrees. They call this the tension force. I guess she's pulling with a string that's attached, or a rope that's attached to the sleigh, and that's the angle that it makes. What other forces do you know that are acting here? Certainly gravity will be acting, so I'm going to put a force downward here. I'm going to label it Fg. While I'm at it, I can write mg, which, since we know there's 47 kilos in here, times 9.8, that's going to give me a value. What have we got here? 47 times 9.8, close to 470, 460.6 newtons. All right. They tell us also, look out, there is friction, probably not a heck of a lot on snow, but some is certainly present. So there's FF. And since I know FF is equal to mu Fn, hey, why not write that in? Now at this point, you might be tempted to write that that's equal to mu mg. But remember, that was in grade 11. You're now in grade 12. This may or may not be the case. You have to analyze the situation on its own merits. So actually, let's just get rid of that. This might be wishful thinking. I'm going to delete that for now. Let's just keep going with what we know before we commit to something that is a mistake. Is there a normal force? Yes. The object, the sleigh, is in contact with the ground, so there will be a response from the ground. Let's make that green, and we'll make it pointing up, just like that, and we'll call it Fn. Okay? We've got all the forces taken care of here, and what we normally do at this point is we go to our components, we write all of the forces that we see, so Ff equals something, comma, something, Fn equals something, comma, something, Ft equals something, comma, something, and finally Fg is equal to something, comma, something. And all of that, all of those somethings have to add up to an Fnet, which is 0, comma, 0. All right, let's fill things in. Let's start with what we know. Fg, which is 0 in the x direction, all of it in the y direction, and for that matter, pointing downward, so negative, assuming positive y like this and positive x like that. How about the tension force? It's going to be something cos 23, something sine 23. If you do SOHCAHTOA, you'll see that the x gets the cos and the y gets the sine. But multiplying times what? We don't know the tension force, therefore it's a variable, and variables can be written in any letter you want, but I'm going to use Ft so that I don't forget what it is I'm calculating. Both of them are positive because of the direction they're pointing. How about Fn? What do we write here? None of Fn is in the x direction, so 0 goes there. All of it is in the y direction, positive, and again, a variable. Why not call it Fn? And finally, Ff, none of which is in the y direction. All of it is in the x direction, in fact, the negative x direction. And I could put Ff here, but actually, using the formula we learned back in grade 11, I can replace that with mu Fn. And at this point, I'm going to leave you free to solve this on your own. You now have two equations, one in the x direction, one in the y direction. Here's your x equation. This plus that plus that plus that equals that. And here's your y equation. This plus that plus that plus that equals that. Write yourself two equations. Will that be enough to solve? Well, let's look at the number of unknowns. Fn is unknown. It appears twice. Ft is unknown. It appears twice. There are two variables, two unknowns. Your x equation and your y equation will be sufficient to solve here. And when you do this, by the way, just check back. Was Fn equal to Fg? Was Fn equal to mg, like it is in grade 11? Or is it a different value? I think you're going to see it's a different value. And for those of you looking for a little bit of a challenge, explain why the normal force was actually less. That's what it's going to turn out to be. Why is Fn less than Fg? That's my challenge to you, to see if you can explain that. There's a very good reason for it, and I'll give you a hint. It's got to do with how Mom is pulling on this sleigh. All right? That's enough for that. We're going to finish off with a question that incorporates friction and inclined planes and some kinematics. So this is actually a little bit of a difficult question for some people. I'll give you some hints and we'll take up the rest in class. However, let's have a look. This one's out of your course pack. I believe it's on one of the last pages. It's a question number 3, although I apologize, I forget which page. You see a ramp, you see a mass m, unknown, an angle of 30 degrees, and a vertical height of 10 meters. Assuming the ramp is frictionless, determine the initial speed that m must have so that it comes to rest at the top of the ramp. Well, that's something that you were supposed to have done in a previous section. I believe this is in section 2.3 in your textbook, which would be lesson 2. That was some homework in there. What I'd like to focus on here is this. Repeat this with friction. So this is section 2.4 in your text, or lesson 3. So this is what we're focusing on. The mass goes up the ramp, and they're asking you, what is the initial speed that you have to give this thing? Just a quick push. Maybe if it was a bowling ball, for example, that you were rolling up a ramp. What initial sort of push with your arm would you have to give it? This is not a push that continues up the ramp. You're just pushing something up a ramp and letting go. You're not pulling it up the whole way. That's important to note. That might not be clear based on the question. So in other words, you give it a push and then you let go. So that it has an initial speed, let's call that v1, so that it comes to rest at the top. So that's going to be a v2 at the top of 0. Other things I notice here, looks like this object has moved a certain distance. Since I see that that's going to happen, I'm just going to point that out, and maybe I'll need to use this, maybe I won't. We'll find out later. Now let's think for a minute. If I told you v1 was what you needed to find, and I told you that v2 was 0, and I told you that you went a certain distance, which by the way you can figure out here. You can use trig. I believe you can say sine theta equals opposite, which is 10, over the adjacent, which is delta d here. So you can find delta d, you know v2, you're looking for v1. Is there a formula that relates velocities and displacements? Well, yeah, kinematics, which is what I hinted at, is what you want to look at. So ultimately what we're going to do is we're going to pick a formula, and if you think about it for a moment, the best formula, which actually has everything we need, is this one. This has v2, it's got v1, it's got delta d. The only thing is you're going to need to know a before you can solve for v1. So really what this question boils down to is, what is a? What is the acceleration when a mass goes up a ramp, an inclined plane? And remember, you're not pushing it all the way up the ramp, you're only giving it a push at the very beginning, and then you're allowing it to slide up itself. Can you think about what would happen if you actually did this? If you actually slid something up a ramp, maybe think of yourself at Wonderland with one of those games where you can win a stuffed animal, where you got to roll a ball up a ramp, and if it lands in one of the holes at the top, you score points, and if you get enough points, you win a prize. If you've ever played that game, it's kind of like what we're talking about here. We're giving a push up the ramp, but the push is only at the beginning. On the way up the ramp, there is no force applied by the thrower or the pusher. So let's just draw this inclined plane one more time. We've got a mass sitting on there. Now thinking back to section 2.3, where we talked about inclined planes, that's where you learned a number of important things about this problem. First of all, gravity, which is straight down, is going to look like this. Secondly, the normal force, normal meaning perpendicular to the surface, is going to look like this. It will not be perpendicular, it will not be straight up and down the way it is in grade 11. So this is yet another problem where the normal force is not equal to gravity. In section 2.3, these were the only two forces to deal with. But in section 2.4, we're dealing with friction. So now we got to realize, as you slide up the ramp here, there is a force holding you back, and that force, of course, is friction. So today, I'm going to be drawing that in to my inclined plane question. There's FF. And if you remember how to deal with inclined planes from the last lesson, maybe you'll remember, in this case, we pick a rotated coordinate system so that the direction of motion is the new x direction. That makes perpendicular to the plane, which is the direction of the normal force, the y direction. Now, I can pick the y direction easily enough. There's y. However, should I make up the ramp positive, or should I make down the ramp positive? Which one? Since the object in this case is moving up the ramp, I'm going to make the positive x direction that way. Therefore, the friction force will actually be in the negative direction this time. The 30-degree angle, which is the angle of inclination of the ramp, that's going to match up with, I'm going to draw it in just 1 second. Here's my y-axis, and here's my x-axis. Remember, the angle of inclination ends up being the same as this angle in here. If you forget why, look back at the previous video. And what this means is that FG has actually got a component, one of which is in the, sorry, let me use blue there, one of which is in the x direction. It's got a little bit of a component backward, and it's also got a little bit of a component downward into the plane, like that. We call this FGY, and we call this blue one FGX. So now, sit back for a moment and analyze what's going on. What have we got going on here? We've got an object trying to fight its way up a hill. Its inertia is carrying it up a hill. However, gravity is pulling it down a hill, like you learned here in section 2.3. But now, today in section 2.4, there's also friction pulling down. Furthermore, friction is equal to mu Fn. And what is Fn equal to? Reminder, I know I keep stressing this, but I can't stress it enough. It's not equal to mg. This is not a situation where the normal and gravity are equal to one another. In fact, maybe you can see that the normal is actually balancing with Fgy. So let's see if we can write something in there for the normal. Do you see how Fn is actually equal to, what is Fgy? It's actually mg cos of 30 degrees, which you learned again back in section 2.3, that the normal force and the gravity force in the y direction, gravity in the y direction comes out to mg cos theta, and therefore if the normal is balancing that, then these guys are equal. So, what have we got in terms of our analysis? Remember how we got started on all this? We're trying to solve for the initial velocity needed to get the object to the top and come to rest. Before we could do that, we need the acceleration. Well, we're about finished here. You'll see in a moment. A, of course, is equal to F net over m. And that means if we just find the net force here, we'll be okay. Well, let me show you a little bit of a shortcut I think you guys are ready for. In the y direction, the normal force and the y component of gravity balance. The only net force is actually in the x direction, and it's in the negative x direction. It's caused by FF and FG in the x direction. So here's a little shortcut for some of you who can see where this is coming from. I've got negative FF, and I've got negative FG in the y direction. Those all have to be divided by mass. What is FF? It's mu Fn. What is FG? Oops, sorry, I realize I just made a mistake. That should not say y, that should say x. Good for you if you caught that. Bad for me for writing it. Okay, but at least I caught it. FGX, that is what? Mg sine of 30 degrees. Again, go back to section 2.3 to see why. Divide this by the mass. And finally, what do you put in for Fn? Well, it's what we realized here. Fn is equal to mg cos 30. So take in that mg cos 30, sub it in there, and in the end, you're going to have, I'm running out of space here, I apologize, mu mg cos 30 minus mg sine 30, all divided by m. That's your acceleration, which you can now sub into this kinematic formula. You know the distance. You know that v2 is supposed to be 0, so now you can solve for v1. All right? And that is all I've got for you today. I know it was a little bit of a long lesson, but these are tricky problems. Just final thoughts before I go. Look at this. M appears in this term and this one, and in the denominator. Factor m out of the numerator as a common factor, and guess what? M cancels numerator and denominator. Are you surprised that acceleration, which is being caused by gravity, doesn't depend on m? You shouldn't be. It hasn't been up till now in the course, unless we're dealing with air resistance, and it still isn't. All right, folks, that's it for today. Hope you learned something new, and I'll see you in class. Thanks for watching.